So folks, in this video we're going to look at solving systems of equations using matrix inversion. We've already learned how to solve systems of equations using matrices through a process called Gaussian elimination or Gauss-Jordan elimination using that row reduction algorithm. This is another way, and that might seem a little bit confusing, but we're actually going to teach a total of 3 different ways to solve systems of equations using matrices, and this is the second one. Before we get into that, I've given you this matrix B here, and I'm asking you to compute its inverse. Just as a reminder, if I gave you matrix A, and I asked you to compute its 2 by 2, it's a 2 by 2 matrix, and I asked you to compute its inverse if it exists, you could either use the row reduction technique that we saw, or you can use the 2 by 2 formula. And I'd like to do that 2 by 2 formula because I have something I want to say about it. If you do the 2 by 2 formula, then we compute the inverse this way, AD minus BC, and then we swap the main diagonal entries, and we change the sign on the remaining entries. So that was our formula. So in our case here, matrix B has an inverse of 1 over 1 times 3 minus 3 times 2. And then I swap the entries on the main diagonal and change the sign of the remaining 2 entries. And if I continue to crunch that, that would give me in the this expression, the scalar multiple, would give me 1 over minus 3 minus 3 minus 2, 1. And if I distribute that through, we will get we will get minus 1, 1, 2/3, and minus 1/3, watching your signs there. The only thing I want to say, the reason why I wanted to do it this way, was I wanted to give a name to this expression right here. Notice that if AD minus BC does not equal 0, A is invertible. We will talk more about this topic. It'll be a standalone topic in this course, but we call AD minus BC the determinant of matrix A. And we denote that one of 2 ways, either as the determinant of A or as the determinant of A, where here I use the abbreviation DET as an operation. We take the determinant. It means to do this calculation here. Or here, these look like absolute values, but it means to take the determinant of this matrix, meaning to do this calculation. So another way we could say this is if the determinant of A does not equal 0, then A is invertible. So now that we've computed the inverse of B, I should be more careful here, folks. I should have an inverse on that. We've computed the inverse of B to be this matrix here. I'm ready to talk about solving a system of equations using matrix inversion. And this is kind of a clever way of tackling this problem. What I'd like to do is I'd like to take this system of equations and convey all of the same information, but as a matrix equation. Now careful, when we did Gauss-Jordan elimination, what we did was we came up with an augmented matrix. This is a different procedure. I'm coming up with a matrix equation. So let's use the matrix equation. Capital B x bar is equal to b bar. I often, when I have my matrices as just column vectors, I'll often write them lowercase rather than capital letters. Okay? Where in this case, B is our coefficient matrix. And it would be the coefficients in front of the variables with the appropriate row and column corresponding to the appropriate variable and equation. So we get 1, 3, 2, 3 for that coefficient matrix. We would call x bar, we would call it the variable matrix, or variable column vector, column. And in this case, our column vector is x1, x2. If I'd used x and y, I would write x and y there. And we will call this column vector b, negative 4, 10. We'll call that the constant vector. So what this means is I can take this system of equations here and convey all of the information in this matrix equation. So in our case, it would be 1, 3, 2, 3. X1, x2 is equal to minus 4, 10. This next part that I'm about to do, I'm going to show it in its gory detail. Usually we will actually manipulate it symbolically, and we will not go to this level of detail. But I think it's important to see how this works. So the strategy that we're going to do is we've already shown the matrix B here, this coefficient matrix. We've already shown that it's invertible, and in fact this is its inverse. So I'm going to take this inverse and multiply it on both sides of this equation. So if I take that matrix equation, 1, 3, 2, 3, x1, x2 equals, give some space, minus 4, 10. Let's multiply both sides by that matrix B inverse, which we computed up above to be minus 1, 1, 2/3, minus 1/3, and minus 1, 1, 2/3, minus 1/3. Now, careful folks, I can only take matrix B inverse and multiply it to the same side of the matrix equation. So since I'm wanting to do something, I want to interact matrix B inverse with matrix B, I need to multiply matrix B inverse on the left-hand side of this equation, so I need to do the same over here. Now we can go ahead and you can do this multiplication if you want. It's always nice to confirm that it checks out. And if you do so, you will end up with the 2 by 2 identity matrix, because that's what it means to be a matrix inverse. When we multiply an inverse by the matrix, we get the appropriately sized identity. On the left-hand side, or excuse me, on the right-hand side, we're going to have to do some matrix multiplication. And if I were to do this here, let's see, if we take negative 1 times negative 4, we get positive 4, and 1 times 10, we get positive 10. And so that gives me 14 for that computation. And here if I do 2/3 times negative 4, I get minus 8/3. And if I do minus 1/3 times 10, I get minus 10/3, which gives me a total of minus 18/3. And that reduces down to be minus 6. So one more time, let's look at this multiplication over here. We multiplied this row by this column, that gave me that entry. We multiplied this row by this column, that gave me that entry. And that all made sense because we were multiplying this 2 by 2 matrix to this 2 by 1 column vector. And the interior dimensions aligned, and we ended up with a 2 by 1, and that's how I found those entries. On the left-hand side, this of course makes sense. We're multiplying a 2 by 2 by a 2 by 1. And you could do the multiplication, or you can remember that when we multiply, whether it's a column vector or a matrix, by its appropriately sized identity matrix, we will always just return what we started with, that column matrix. So in here, I get x1, x2 is equal to 14, negative 6. And the beauty of this is I've now given the solution to this system of equations, i.e. we've shown that x1 is equal to 14, and x2 is equal to negative 6. So I would prefer to leave the answers in these vector forms. But if you wanted to, you could also leave it as an ordered pair. The ordered pair solution to the system is 14, negative 6. So folks, in this case, we had a system of equations. We have many ways of solving systems of equations, and you've learned 2 or 3 methods using algebra. We've now learned one. We had previously learned to solve this system of equations using Gaussian elimination with matrices, and now we know how to solve it using a matrix equation if we've got an inverse matrix. One thing to comment on is that this only applies if you can compute the inverse, and not all matrices have inverses, especially matrices that aren't square matrices do not have inverses. So this only works if the number of equations equals the number of rows, and you're in a situation where you have a unique solution because that inverse matrix exists. We'll talk more about that in class when we start looking at the big theorem of linear algebra. But again, I wrote the system of equations as a matrix equation, and then I multiplied both sides on the left by the inverse of that coefficient matrix. And just by doing multiplication, then, I was able to give the solution to the system. I hope that clarifies, and I'll see you in the next video.